is from GATE 2020 for 2 marks. A resistor and a capacitor are connected in series to a 10-volt DC supply through a switch. The switch is closed at t equal to 0 and the capacitor voltage is found to cross 0 volt at t equal to 0.4 tau, where tau is the circuit time constant. The absolute value of percentage change required in the initial capacitor voltage if the zero crossing has to happen at t equal to 0.2 tau is. Okay. So the first problem is from GATE 2020 for 2 marks. A resistor and a capacitor are connected in series to a 10-volt DC supply through a switch. So we have a resistor and a capacitor. They are connected in series through a 10-volt DC supply. They are connected through a switch. The switch is closed at t equal to 0 and the capacitor voltage is found to cross 0 volt at t equal to 0.4 tau. So I am giving my capacitor voltage polarity as shown in the figure. So now this Vc is found to cross 0 volt at t equal to 0.4 tau. So my x-axis is time axis. So from at t equal to 0, I turned on the switch. So now current will start flowing through the circuit. It is observed that the capacitor value, the capacitor voltage value is found to cross 0 volt. It means initially the capacitor voltage was negative. If this is the polarity of capacitor voltage, we know that at the end of finally what will happen? The capacitor will attain this voltage. Hope you are familiar with RC circuits connected to a DC supply. So when RC circuit is connected to a DC supply, the capacitor will keep on charging until it reaches the steady state value. So you know that finally the capacitor value will be 10 volt. But initially you don't know how much. But it is given in the problem that the capacitor voltage is found to cross 0 volt. So this will happen only if the initial capacitor voltage is negative. Is this point clear?
Yes, ma'am.
Okay. So capacitor voltage will cross 0 volt at t equal to 0.4 tau, where tau is a circuit time constant. The absolute value of percentage change. So initially capacitor voltage was some negative value. Let it be capacitor initial voltage 1. So that value we don't know, but it will reach 0 volt at 0.4 tau. Now what we have to find? The absolute value of percentage change required in the initial capacitor voltage if the zero crossing has to happen at t equal to 0.2 tau. That means if the initial value of capacitor voltage was another value, it will reach 0 volt at 0.2 tau. Now if it has to reach 0 volt at 0.2 tau time, then what needs to be the initial capacitor voltage? And what we have to find? We have to find the absolute value of percentage change required to, percentage means absolute value into 100. So absolute value of percentage change required in the initial capacitor voltage. So percentage change, that means Vi1 minus Vi2. Initially we know that it was Vi1. So percentage change means the difference between Vi1 and Vi2 divided by Vi1. So we don't know whether this value is positive or negative. That is why it is given that, that is why it is given that we have to find absolute value. Sorry. Okay. Is this clear what we have to find in the problem?
Yes, ma'am.
Okay. Now we have to find what is Vi1 and Vi2. Then we have to solve this. Now you know that for a first order system, the output is equal to the final value of the output plus initial value of output minus final value of output into e raised to minus t by time constant of the system. Are you familiar with this relation?
Yes, ma'am.
Okay. So do I have to explain by taking an example?
No, ma'am, you can solve further.
Okay. So in this given problem, we have to, this is a first order system, RC circuit. Capacitor and inductance are memory elements. Resistor is not a memory element. So any combination of capacitor or resistance or just capacitor alone is a first order system. So now, in this given question, the output we are interested is in capacitor voltage. So capacitor voltage at any time t is the final value of capacitor voltage plus initial value of capacitor voltage minus final value of capacitor voltage e raised to minus t by tau. The time constant of an RC circuit is R into C. But anyways, in this problem, we won't be needing RC product. So let us look what we all know. So this graph we'll take. I'll draw it once more. When the capacitor initial voltage was 1, it will reach 0 volt at 0.4 tau. When it was the second case, the initial value is Vi2. It will reach 0 volt at 0.2 tau. So these two conditions will equate in this given equation. So in the first case, the capacitor voltage at 0.4 tau, Vc of 0.4 tau is, we know it is already 0. It is equal to final value of capacitor voltage is what? The applied voltage. In a DC circuit having an RC element, the capacitor voltage final value will be the value of the DC voltage. So final value is 10 plus initial value is Vi1. Vi1 minus final value is 10 e raised to minus 0.4 tau by tau. So this is our equation number 1. Now what is equation number 2? Capacitor voltage at 0.2 tau, which is the second case. Its value is also 0, which is final value plus. In this case, the initial value is Vi2 minus final value e raised to minus 0.2 tau by tau. So this is second case. When you solve the first equation, you will get Vi1 as minus 10 by e raised to minus 0.4 plus 10. Is this correct? So you'll obtain Vi1 as minus 4.918 volts. By solving second equation, Vi2 will be minus 10 by e raised to minus 0.2 plus 10, which is minus 2.214 volt. So now you have Vi1 and Vi2. When you find the difference, divide it by Vi1, multiplied by 100, you will get the answer as 54.98%. Is this clear, this problem?
Yes, ma'am.
Okay. We'll move on to the next problem, which is from GATE 2019 for 2 marks. In a DC to DC boost converter, the duty ratio is controlled to regulate the output voltage at 48 volt. The input DC voltage is 24 volt. The output power is 120 watt. The switching frequency is 50 kilohertz. Assume ideal components and a very large output filter capacitor. The converter operates at the boundary between continuous and discontinuous conduction modes. The value of the boost inductor is. Is the problem clear? Hello?
Yes, ma'am.
Okay. So we have a DC to DC boost converter. So here it is given that the input voltage is 24 volt and the output voltage is 48 volt. So we know for a boost converter, the output voltage is input voltage by 1 minus D, where D is the duty ratio. So in this case, your output voltage is 48, input voltage is 24 by 1 minus D, your duty ratio will come out to be 0.5. Let I not be my output current. IL is the inductor current. And IS is my current through switch. Now it is given that The output power is 120 watt. Output power is V0 into I0, where I0 is the average value of small I0. So this is given as 120 watt. So V0 is 48, I0 we don't know, which is 120. So you'll get I0 as 2.5 ampere. So from these three sentences, we obtain D and I0. The switching frequency is 50 kilohertz. Assume ideal components and a very large output filter capacitor. So very large output filter capacitor means the average current through the capacitor is 0. Also, the DC voltage is maintained constant at 48 volt. The converter operates at the boundary between CCM and DCM. So you know that when the the voltage across inductor is positive, the current through the inductor rises. And when the voltage across inductor is negative, the current through the inductor falls. So in this case, the inductor is operating at the boundary of CCM and DCM means the minimum inductor current is 0. So in general case, you have a minimum inductor current and a maximum inductor current. When it is operating at the boundary of CCM and DCM, the minimum inductor current is 0. Let delta L be the peak-to-peak ripple current of inductor. So at the boundary of CCM and DCM, your maximum inductor current will be delta L. Is this clear?
Yes, ma'am.
Okay. So in this case, what is the value of inductance is the question. So once you know the waveform of inductor current, you know that the inductor voltage will be positive when the current is rising and negative when the current is falling. So these values to obtain, we will solve for the circuit, when the circuit is on and when the circuit is off. So when the switch is on, the inductor voltage is same as input voltage. When the switch is off, the diode will be conducting. In this case, the inductor voltage will be input voltage minus output voltage. Since we know that in a boost converter, input voltage is less than output voltage, this value will be negative. So this is your inductor voltage and inductor current. So now you apply basic equation of inductor voltage. Voltage across inductor is L di by dt. So when it is conducting for a time period of dts, the inductor voltage is same as input voltage, 24 volt, which is L di. L di. What is the change of current? Change of current in that interval is delta L by time period is dts. So you obtain inductor value as 24 times dts by delta L. So you already found D. You have TS as 1 by Fs, switching frequency is already given. You have to find delta IL. To find delta IL, you already know I0. So from I0, how will you find delta IL? So you know that the inductor current is going through diode as well as switch. So this is the inductor current. Diode current is same as output current and this is switch current. So by applying KCL, you know inductor current value is output plus switch current. So there is one equation which holds true in the case of boost converter is, first you have to equate what are the relation between average values of this quantity. So average inductance value is say IL, capital IL. Average output current is capital I0. Average switch current is say IS. So instantaneous relation between them you already know. But what is the relation between the average values? That you can do as an exercise, the proof we can do as exercise. I will give you the final result. The average value of inductor current multiplied by a factor will give you the average value of output voltage. Similarly, output current. Similarly, the average value of inductor current multiplied by another factor will give you the average switch current. So this factor depends on how much time the inductor current flows through that component. Say in this case, in the case of boost converter, the inductor current flows through the output in how much time? When the switch is closed, the diode will stop conducting. So all the inductor current will flow through the switch for a time period of dts. But when the switch is off, when the switch is not conducting, the diode will start conducting. So at this point, that is for 1 minus d times ts time duration, all the inductor current will flow through the output current. Is this clear?
Yes, ma'am.
Okay. So this relation between them is how much time the inductor current flows through the output. So in the case of boost converter, you already know when the switch is off, the inductor current will flow through the output. So that duration 1 minus d times ts by ts will cancel out. So 1 minus d is the factor in the case of output current. In the case of switch current, the inductor current will flow through the switch during dts duration. So the factor is d. So this is a relation between the average values of inductor current and output as well as switch current. So in our question, we already got my average output current. So my average output current is 2.5. Also D is 0.5. So from this relation, you will get the average inductor current. The average inductor current will be obtained as 5 ampere. Is this clear?
Clear, ma'am.
Okay. So you got average inductor current. Now you already know the inductor current waveform as this is delta IL. This is average inductor current. So the average inductor current is 5 ampere. So what is my peak to peak ripple? You can find the area under the graph. Area under the graph will be your average inductor current, which is area under the graph divided by total length under length. So this is half, this is a triangle. So this is half, base is Ts, height is delta IL divided by the length is Ts, which means the inductor current IL is half times delta IL. So this is a relation between average inductor current and peak to peak ripple. This is general for in the case of CCM and DCM. At the boundary of CCM and DCM, always the peak to peak ripple inductor current will be twice the average value. This is true for all converters, all DC to DC converters. So here you got IL as 5 ampere. So you will get delta IL as 2 times IL, which is 10 ampere. So in this equation for finding the inductance, you got delta IL as 10 ampere. If you solve this equation, you will get inductance as 24 microhenry. The question asked is in microhenry, which is obtained as 24. Is this clear or should I explain once again?
Clear, ma'am.
Okay. So by this, our today's session comes to an end. We'll meet you on next Thursday. Thank you.
Thank you, ma'am.